Let's see. So we have our Newton's three laws. The first law, as your book calls it, is the law of inertia. And so we need to define what is inertia. Um, Inertia describes an object's tendency to stay in its state of motion. Hopefully that doesn't sit very well with you. Hopefully you sort of look at that and it's like, well, that's just Newton's first law, because Newton's first law says that an object in motion will stay in that state of motion, and then we sort of say, well, that's because of inertia, and so it seems sort of like a circular argument that Newton's first law exists because of inertia, but inertia is really just a restating of Newton's first law. But it is true nonetheless that inertia is a measure of an object's tendency to stay in its current state of motion. So an object with a lot of inertia will tend to stay doing whatever it's doing, and it's going to be very difficult to get it out of that motion. So, for example, a car, or no, like a big heavy piece of furniture has a lot of inertia, it has a lot of mass, and so it's going to be difficult to get it moving. Whereas a small thing, like a little bug or whatever, has a small amount of mass, and so it's a lot easier to get it moving. Inertia is kind of a mysterious thing. Like, we don't really understand why it is what it is. In fact, there's this story about this famous physicist, Richard Feynman. You ever heard of Richard Feynman? Yeah, he won the Nobel Prize back in the 90s. He was also pretty instrumental in the Challenger incident. Y'all probably don't remember that, but it was in 1986, I think, where the Challenger space shuttle blew up. There was a teacher on board. You've heard of it, I think, maybe? Yeah, so anyway, he was instrumental in figuring out what happened on that incident. But Richard Feynman, when he was a kid, he asked his dad, why does, when he pulls his little red wagon, why when he pulls his wagon does the ball inside of the wagon move to the back of the wagon? Right, so I have a wagon and I'm pulling it, and there's a ball inside it. When you pull it, the ball moves to the back of the wagon. Richard Feynman, a little kid, asked his dad, why is that? Why does the ball move to the back of the wagon? And his dad says, well, it's because of inertia. And he said, well, what is inertia? He said, inertia is that thing which causes the ball to move to the back of the wagon. Right? So it's a circular argument. We don't really know why it is that mass does what it does. And there's a lot of really cool research into the interaction between masses, even today, that people are studying this. But nonetheless, it is what it is, and we can observe it. Now I'm going to show you a magic trick. Are you all ready? Here I have two masses. Right? This one is 10 grams, and this one is 100 times bigger at 1,000 grams. This is a what? This is a kilogram. This is like that cylinder in France. Right? And now I'm going to put them behind my back, and I'm going to ask you to tell me which one is in which hand. Right now they're in these hands. This is my left, this is in my right. But I'm going to put them behind my back. I'm going to jumble them around a little bit so you don't know which is which. Okay? And now I'm going to demonstrate something to you. You can't see them. They're going to be in my hands, and you're not going to be able to see them, but I want you to tell me which one is which. Okay, you ready? I'm not going to show it to you. I'm going to keep it hidden in my hand, but I'm going to do something. And you should be able to tell with magic which one is the 10 gram and which one is the 1,000 gram. Are you ready? Are you ready? Okay. All right, here's one of them. You want to see the other one? You don't know which one that was, right? Because you couldn't see it. It was in my hand. And now the next one. Which one is in my left hand? That's this hand over here. The 10 gram. But you couldn't see it. Which one is in my right hand? But you couldn't see it. Well, maybe you could see it, but you couldn't see it. How do you know which is which? Right, because it's a lot easier. You were right. Very good. This was the 10 gram. It's really easy to move around, but the 1,000 gram is very difficult to move around. Okay? It's not because of their weight. We'll talk about weight later, and weight is related to the mass, but it's not about the weight, right? It's about the mass. In fact, if these were weightless, the same thing would happen. As a kid, I used to think if I was up in space on the space shuttle and everything was weightless, it is, right? The space shuttle in space is weightless. It has no weight. There's no force weight acting on it. It's weightless, right? And I sort of had this idea that if I was up in space and I pushed on the space shuttle, it would go flying off into space because it's like the 10-gram mass, and it's really easy to move. But that's not true, right? Because the space shuttle has a lot of inertia. It has a lot of mass. And so if I push on it, nothing's really going to happen to the space shuttle, even though it's weightless, because it still has a lot of mass. All right? You can do this little magic trick with your friends, or maybe like if they're little friends about this tall, and they'll say, wow. Y'all look less amazed by it, but I think it's fairly amazing, because inertia is a really cool thing. All right? All right, so let me just sort of write this down. Mass is a measure of inertia. I said that, but let me just make sure it's clear. That mass is a measure of inertia. So an object with more mass has more inertia. And then let's just write the first law. The first law is the law of inertia. Inertia is this. Mass is how we measure that inertia. But the first law says that an object will tend to stay in its current state of motion. Whether it's moving or not moving or whatever. What would Aristotle say is this law of motion? An object will do what? An object will do what? It'll what, Shelby? It'll come to rest. If an object's moving, it's going to come to rest. If it's at rest, it's going to stay at rest. Aristotle, in fact, most of the people in the world today walk around thinking like Aristotle, say that an object will tend to move into a state of rest. All right, the second law, can I move down from here, y'all? Yeah. All right, the second law is the law of acceleration. It's more of a mathematical thing. Actually, it's going to be related to momentum. Oh, no, we're not doing momentum in this class. I'm sorry. But when Newton wrote it, he wrote it a little bit differently from this. But he said that the acceleration of an object is proportional to the force. That is, A is proportional to F and inversely proportional I'm going to abbreviate that, proportional to the mass. That is, A is proportional to, I'm sorry, not the mass, the inverse of the mass, to 1 over m. A is, no, I'm sorry, never mind, inversely proportional to the mass. Very, very sorry. That's correct. But when I say that something is inversely proportional, I mean this, that A is proportional to 1 over the mass. That's what the inverse means. All right, so this comes about, of course, famous equation. If I put these two proportionalities together, solve for F, I get F equals ma. Now, typically people think that if I apply a force, that I cause an object to get to a certain velocity, and that's what they were talking about in the video with the incorrect laws of motion, that if I apply a force to an object, it will move up to a certain velocity, and then it will travel at that velocity for a certain amount of time, right, as long as I'm applying that force. But this is saying something that's quite different. that the force, if I apply a force to an object with a certain amount of mass, it's going to increase in its speed. Increase, 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 increase. Always, 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 as long as I'm applying that force. All right? And then the third law, this is the law of acceleration. The third law is the law of reaction. It says for every force, there's an equal and opposite force. An equal and opposite force. For every force that exists. Now that should sort of blow your mind, that any time I exert a force, then there must be an equal and opposite force that exists. It also means that there can never be an isolated force, that there is never a single force, never, never, ever, ever is there a single force that's operating or that's functioning, that's exerting onto an object. There can never be an isolated force. So, like for example, have you ever been in a fight? Who's been in a fight before? Like a fist fight? Paige, you've been in a fight? No. Okay. I got into a fight once. It was like 8th grade with Nelson Zamora. Does anybody know Nelson? He's from Mississippi. We're friends now. I mean, we're not friends, but later we became not really friends. No, we were never really friends. He was kind of a jerk. Maybe I was a jerk too. But anyway, we got in a fight in 8th grade, and it was sort of very, what's the word? Typical of childhood things. Like we made a plan to meet after school. I'm going to get you. I'm going to get you. And then we met at this park after school. It's like, all right, let's get started. And then we got in a fight. And then afterwards we shook hands or whatever. And then we went our own ways. But I'm not advocating that you go out and get into fist fights by any means, because you shouldn't really do that. That's not good. But he and I got into a fight. And when we punched one another, exerted a force, either he or I forget, exerted a force onto our face, right? Now, I'm exerting a force onto my face, where is the reaction force? So the third law says that for every force, there's an equal and opposite force. If I'm getting punched in my face, what is the reaction force in that case? Okay, there is a reaction, like your face is turning. But what this is saying, this law, is that anytime I have a force going in one direction, I have an equal and an opposite force in the other direction. So what is the force in the opposite direction? If I'm punching, I have a force going in this direction on my face. What is the other force? Right, have you ever been in a fight? Your fist hurts, right? Because you have this other force that's pushing back on your fist. Not that y'all have been in fights. And you shouldn't get into a fight. But it's a good example of this action-reaction pairs, that we have an action force, that is, something striking a surface, and then the surface strikes back, basically. Okay? We'll see that this third law becomes fairly important in some of the forces that we'll talk about in this chapter, particularly the normal force, which we'll see right now, I think. Yeah. So let's look at some different types of forces. This book goes through each of these types of forces. The first is weight. So anything that is on the surface of the earth, this is the earth, this is me, I'm standing here, I have a certain mass. My mass is roughly 70 kilograms, right? That's sort of a typical male, is about 60 to 80 kilograms, right? So my mass is about 70 kilograms, but remember, that's not the same as weight. By the way, if I'm measuring something in pounds, what is that a measure of? Is that a measure of your mass or your weight? Y'all know? It's your weight, right. So when you measure something in pounds, that's not a measure of your mass, that's a measure of a force, right, which is your weight. Do y'all know and pounds is the British system. We're going to use a different unit for force. But do you know what the unit is for mass? This is just interesting. You don't need to write it down, but you will amaze your friends. Now, grams is also in the SI system. There are subsystems within the SI system. We use the MKS, meters, kilograms, seconds, but there are also subsystems like the CGS, which is centimeters, grams, seconds. So it's not grams, but good try. Anybody know? I don't think any of you are going to know. The unit for mass in the British system is the slug. And that's kind of like our kilogram in the SI system. I think it's a lot cooler to say my mass is so many slugs. And I don't even know what my mass is in slugs, but I'm going to go find out so I can come back and tell y'all how much my mass is in slugs. Okay? All right. So anyway, your mass and your weight are different. Now, so if my mass is 70 kilograms, there is an attraction between me and the Earth. So the Earth pulls down on me with a certain force. That force is the weight, and that force weight is equal to the mass times what we're going to call g, which is the acceleration due to gravity. Let me double check. I'm not sure if your book calls that g. Does anybody know? Have y'all? Let me just look. They do call it g. Okay, in your book, they give this a value of 9.8, but we're going to just make it a little easier. Instead of saying that it's 9.8, which is what they do in your book, we're just going to let that be 10, and it's going to be an acceleration 10 meters per second squared. So remember Newton's second law? What was Newton's second law? The equation that resulted from it. F equals ma, right? This is just a rewriting of that F, but we're looking at a weight here, is equal to the mass times a particular acceleration, which is 10 meters per second squared. This comes about because all bodies of mass have a force that is attractive. So all of you are sitting out there, and all of you are feeling forces between you and the other students. Weird, but true. It is true. They're small forces because your masses are fairly small, but nonetheless, it's true. And so in a similar way, the Earth, which is a really big mass, has an attractive force on you, which are really small mass. Now, where is the reaction force? So Newton's third law says that if I have any force, there has to be an equal and opposite force. So if the Earth is pulling down on me with a force equal to 700 newtons, I'm going to tell you the unit for that, 700, what is the reaction force? What is the equal but opposite force? That's right, Carly. Carly, right? Yeah, so that's right. So not only is the Earth pulling on me, but I am pulling back on the Earth. So the Earth is pulling down on me with a force weight equal to 70 kilograms times 10 meters per second squared. That's 700 newtons. And likewise, this is my weight, 700 newtons. And likewise, I'm pulling up on the Earth with a force of 700 newtons. So take that, Earth. It's pulling down on me, but I'm pulling right back up on it. Okay? All right. Let's watch a little video, and then I'll show you. We'll do some of the other forces. All right. All right, so let's look at a couple of other different forces. Actually, first, before we do that, I want to look at something called a free body diagram, or net force. We'll first define what is the net force. The net force is the vector sum of all the forces. Let me first define what is a vector. A vector is a quantity that has a direction. So for example, forces are vectors because they have a certain quantity, we call that a magnitude, and then they also have a direction. They're to the left, they're to the right, they're up, they're down, they're back, they're forth. All right, so that's a vector quantity. There are other things that are quantities that don't have directions. For example, what's a good quantity that doesn't have a direction? That we've been talking about a lot, actually. Okay, time, right? Something else there. Just watch the whole video on it. Inertia or mass, right? We call those scalar quantities. They don't have a direction attached to them. But some quantities do have directions attached to them, like, for example, forces. And we represent vectors as an arrow. So say, for example, I had a force that was 3 newtons. So I don't think I told you the unit for the force, but the unit is the newton, named after Isaac Newton, of course. Because it's a name, you lowercase when you write out the word, it's uppercase when you abbreviate it. So I have 3 newtons, so I can have a force in that direction, or I could have a force in this direction, say 2 newtons in that direction. Now, when I say the vector sum, what that means is I'm going to give some of the directions a positive quantity and some of them a negative quantity. Now, in our world, because we use, don't write this down, but we use a right-handed coordinate system, and in the right-handed coordinate system, which sort of looks like this, we let right be positive and left be negative. All right? I don't know why it is. If it was a left-handed coordinate system, it would be the opposite. So we have, in this case, I have a positive 3 and a negative 2. So if it's to the right, it's positive. If it's to the left, it's negative. If it's up, it's positive. If it's down, it's negative. Those are just the notations that we use. Right and up are positive, left and down are negative. You'll see this in your coordinate system too, like in your XY coordinate system. This is positive, this is positive, this is negative, this is negative. So you probably know that. It probably makes intuitive sense to you because we live in this right-handed world. We have a right-handed coordinate system. Okay? So the vector sum just says I ascribe these directions, and then I can just add them up. So the vector sum of these two forces would not be 5. It would not be, what would the vector sum be? It would be 1. I would say 3 minus 2 equals 1. Now, vector sums can be a bit more complicated than that, especially if you have vectors that are not on an x or a y axis. But we're just going to deal with one-dimensional force vectors here. Okay? So that's how we find the vector sum. And then also, I can draw, let's say that I have an object. Can I go down from here, y'all? Let's say that I have an object, say a block that sits on the table. I have some forces acting on it. First of all, let's say that I have a force where I'm pulling in this direction. So I have a force I'm pulling in that direction. I have the weight that's acting upon this block. I can also know by Newton's third law that I'm going to have another force that's pulling up. I'm going to call this Fn. I'll define what that is in just a bit. Fn. And then let's say that I also have a frictional force. I'll just call it lowercase f. What I've done here is I've drawn a free body diagram. It's just a picture of an object with all of the forces labeled. All right, I just take a single object and I label all the forces. So this is a free body diagram for this particular object. And we'll be doing this probably not today, but next time. But this is a free body diagram and all the forces that are acting on this object. All right, let's do a few questions now, and we might have some more time to come back to this. Sort of questions about Newton's laws and how objects act. So here I have a book. It's lying at rest on a table. The book will remain there at rest because which of these options? A, B, C, D, or E? Why will the book remain at rest? Ask your neighbor as soon as you get an answer. Remember, the net force is the sum, the vector sum of all the forces that are acting on that object. You would say that if there are forces, but they all add up to zero, that there is no net force, or there's zero net force. Okay, ask your neighbor, but most of you have it wrong, so you probably have it wrong. I think I might have misled you a little bit. We'll see. All right? Yeah, some of you are better. So I'm going to stop at 155. 155, just guess if you don't know. Okay, good. That's a lot better than it was a few seconds ago. But D is the right answer. There is no net force. So Newton's first law, an object will tend to stay in its current state of motion. Did I add an extra little clause to that? I think I might have. I might not have written it. Unless a force acts upon it. Okay, make sure that you got that. Is that in your notes? Okay, yeah, that's pretty important. But an object will tend to stay in its current state of motion unless a force acts upon it. Make sure that's clear. So this object does have inertia, and that's why it has this, it's going to stay in its state of motion, but it remains there at rest because there's no net force on the book. That if there was a net force, then it would move. Okay, so we can draw our free body diagram. Let me go back up. Draw our free body diagram. I have this book. It's sitting on a table. I only have two forces that are acting upon it. The force weight and the force, this is going to be the normal force, the table pushing back up on it. We'll see more about that later. The sum of those two forces, because of Newton's third law, is going to be zero. And so it has no net force. All right, a hockey puck slides on ice at constant velocity. What is the net force acting on the puck? Constant velocity or constant speed. Now, if something has constant velocity, what does that say about its acceleration? Remember, acceleration describes how the velocity is changing. So if it has constant velocity, what does that say about the acceleration? And by the way, I'm going to put these up on the website after we complete them, so you don't need to write them all down. You'll get them. The net force here is the sum of all the individual forces that are acting on this hockey puck. It's moving at a constant velocity. What is the sum of all the forces acting upon it? The vector sum. Okay, ask your neighbor, but only one person has it right, so your neighbor's probably wrong, unless you're really lucky. All right? Yeah, still only one person has it right. Still. Okay, I'm going to stop at 155. 155. E is the right answer. We can draw a free body diagram. And what did y'all put? C was your main thing? Yeah, see, you're still sort of thinking Aristotelian, because you're thinking that if something's moving, there must be a net force acting upon it. And that's just not true. That if something is moving, it might have a net force on it if it's increasing its speed, if it has an acceleration, but otherwise, it doesn't have to have a net force. And in this case, oh, this is a hockey puck, not on a table. So I have a hockey puck. It's sliding across ice, so there's very little frictional forces. It's sliding, say, in this direction. My velocity is in that direction, or my speed. The only forces that are acting upon this thing are the weight of the puck, and then the force, the equal and opposite force that the ice is pushing back on the puck. But otherwise, there are no other forces. And I know that by Newton's second law, which says that the sum of the forces are the net force, right, net force, that the net force is equal to the mass times the acceleration. And so, since I have a constant velocity, that means that my acceleration is 0, and so the net force has to be 0. All right? Sort of makes sense, I guess, but obviously it doesn't make that much sense, right? Everybody would have got me. Okay, so it's moving at constant velocity, so it's not accelerating, so there must be no net force. And then the other forces are that weight of the puck and also the force of the ice pushing back up, which is a force we'll call the normal force next time. You put your book on the bus seat next to you. When the bus stops, suddenly the book slides forward off the seat. Why does it do that? Ask your neighbor. Y'all are pretty confident about your answer, and I appreciate the confidence, but only one person has it right. Okay. Because you're all a bunch of little Aristotelian thinkers. That's what you're thinking, like Aristotle, not like Newton. That's a lot better. Ask your neighbor. Okay, I'm going to stop at 1:30. 1:30. Okay, B is right. All right, so listen. Imagine that you're sitting on the bus. Like, you're in the bus. We're all on the big yellow school bus right now. We're driving along. I'm like the mean bus driver, right? And I start yelling at you, y'all better sit down. You better shut up. Da, 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 da. Did y'all have mean bus drivers when you were in school? I did. Miss Evelyn Burke, man, she was mean. You know? Anyway, I could go on for a while. She had good reason to be mean, because kids on that bus, man, they were bad. Not me. But anyway, the book slides forward, so she slams on the brakes, and the book slides forward off the seat. How has its state of motion changed? The book. What is its state of motion before she slammed on the brakes? It wasn't at rest. What was its state of motion? It was going the same speed as the bus, right? It was moving along at 30 miles an hour, or whatever the bus was doing. And then the bus stops, but the book keeps moving, right? What would have caused the book to stay on the seat? Like, what if I said instead that the book stays on the seat? What would be the reason for that? Because a net force would have had to have acted upon it, right? So, in this case, it's a nice illustration of Newton's first law, that an object in motion will continue in that state of motion unless a force acts upon it. And since no net force acts upon it, that means it just slides right off the seat. Now, usually in a bus, it doesn't slide off the seat, right? Because you have a force that we'll call friction in a little bit. But here, the answer is B. Did I mark B correct? you kick a smooth, flat stone out on a frozen pond, the stone slides, slows down, and eventually stops. Which of these do you conclude? Think about the forces that are acting upon the stone as it goes along. Ask your neighbor when you get an answer what they put. By the way, if your neighbor always has the wrong answer, you can change seats next time. Get a new neighbor. Okay? Doing a lot better on this question. A lot of you have it right, but still about 5 or 6 of you have it wrong. Ask around. How is the velocity of this object changing? Is it changing or is it not changing? The velocity? Okay, it's slowing down. That means that it's changing. It's getting smaller, right? It is going, I don't know, 3 meters per second, and then it's going to 1 meter per second, and then it's 0 eventually. So it is slowing down. So the velocity is changing, which tells you something about the acceleration. All right, I'm going to stop at 158. 158. Okay, we're doing a lot better. C is the right answer. And A is sort of the classic Aristotelian way of thinking. So those 5 of you, it's okay to have a problem, but we need to admit that we have a problem, okay? That you're still thinking like Aristotle. And you know, everybody thought that way for hundreds of years, and still most people think that way today. But we need to move beyond that. That the reason that this thing stopped is not because the force that was pushing it stopped. There was never a force pushing it. Although Aristotle would say, if you have something moving, there must be a force pushing it, because it doesn't do that naturally. That's what Aristotle would say. The reason that it stopped is that it had a force that acted on it to stop it, not to keep it moving. And that force is something that we'll call friction. We'll get to next time. Let's do a few more. Consider a cart on a horizontal frictionless table. Cart's given a push and released. What will happen to the cart? It's flat. There's no friction like we had in the previous problem. You give it a little push and it's released. What will happen to the cart? Doing pretty well. Ask your neighbor. Still about 6 of you without the right answer. Think about what is the net force on this cart. What is the net force? Like after it leaves your hand, what is the net force on it? What's the net force? What are the forces acting upon it? The weight, right? The pull down. And then that other force of pushing back up again. What's the sum of those 2 forces? They cancel, right? Because of the third law. Upward force is equal and opposite to the downward force. Are there any other forces? No. So what's the net force? 0. The net force on this object is 0. Right? So if I have a net force that's 0, what's going to happen to the cart? Will it slowly come to a stop, continue with constant acceleration, continue with decreasing acceleration, continue with constant velocity, or immediately come to a stop? And I'll stop in about 3 seconds. 156. D is right. Continue with constant acceleration. Now, by Newton's second law, if we say that the sum of the forces equals mass times acceleration, I'm sorry, that's the same as saying the net force. Let me just write net. The net force is the mass times the acceleration. We've already said that this is 0, so 0 is equal to the mass times the acceleration. So therefore, the acceleration must be 0. If the acceleration is 0, what's happening to the thing? Keeps on going. So D is the right answer. This cart will continue on forever, or until a force acts upon it. All right? Y'all hang in there. I know it's been a long class. We'll just have one or two more. Because you know what my goal in life is, right? What's my goal in life? Never to let you out early. People just get confused when you let them out early. All right, so what do you have to do in order to make this cart move with constant acceleration? You just push it really harder right before it releases, push the cart for a longer amount of time right before it releases. You have to push the cart continuously. You change the mass of the cart, make it lighter or make it heavier, or can you not make it move with constant acceleration? Okay, y'all doing a lot better on this one. Let's stop soon. Say 110. And the answer is C. If you want to have constant acceleration, you have to provide a net force. It is 10:19, but we'll call it a day. I'll see y'all next week. Remember, quiz at the beginning of class. So please be on time. Please even be a few minutes early. Oh, and by the way, I didn't say this before, but if you miss a quiz, we have so many drop quizzes. Like we're going to have at least 2 or 3 drop quizzes. We'll just sort of, slide it under the rug. You have a good day, okay?